example on page 25, which says we're given a line in vector form. We're given the plane in vector form. We have to see that the line is parallel to the plane. I don't think I have enough time to finish this example, but I'll give you some. This is the example I did last year. I will put the video solution to this example on the website anyway. You also have the handwritten solution to that. I just brought this example on the screen because I want to have like a general discussion what happens when you look at the plane and the line and you don't have the Cartesian equation straight away. In this case, of course, because it's a three-dimensional setting anyway, you can convert this to the Cartesian and have some advantages from that. But if, for instance, each of these columns had another number in it, so it was a four-dimensional plane, you no longer have the luxury of doing the Cartesian argument. You have to deal with the vector form, and that's why I want to show you this example. So normally, the argument which you have to follow is based on the following observation. I'll convert this to the symbolic form. Let me just call this vector A. So this one I will abbreviate with the A symbol. This one will be B, and this will be C. Okay? And I have to give a name to this as well. Let me just call this A1. Okay? The test for being parallel between a line and a plane, the test which you have to try to see if it works or if it doesn't, the test which you have to try to see is this one. If the A vector, this directional vector of the line, can be expressed as a linear combination of the vectors in here. I don't know if you saw this Greek letter. This is a Greek letter nu. This is obviously mu. This is a lambda. So in the course of this solution, the actual numerical solution is in the handwritten solution which I published, in the video solution which I will publish. But you have to keep in mind that the principal idea behind that solution, the principal idea is this test. Whether we can express the directional vector of my line as a linear combination of the directional vectors of my plane. If we can, this is a clear case for the parallel setting between the line and the plane. In case you want to test that the line intersects the plane, L intersects P. In case you test for something like this, look what you have to do. You have to look into the vector equation like this. You have to take the vector A1, this vector, and you can see if you can express this vector as a linear combination of all three A, B, and C. So you have to see if you can express this vector as a linear combination of A, B, C. Again, if you just plug in the numbers, there will be a column of numbers here, column of numbers here, column of numbers here, column of numbers here. If you equate things in a per component way, you will have three equations with three unknowns. This is easier to solve. I'm not saying it's solvable all the time. No, it's not. But it's easier to solve. And that reflects the fact that in three dimensions, it is more often that the line will intersect the plane rather than be parallel to that plane.